Hello from sunny Helsinki. It's nice to be here and great to hear that there's so many countries on board. Because fun fact, I used to work at the United Nations for the Atomic Energy Agency, and we had a team where there was 11 people and not a single one was from the same country. And I loved that sort of multicultural fit to doing technology. So this is rather promising. Let me share my screen and we can kick off. I suppose that works. So we're going to kick off by discussing breakthroughs in applying data science to business initiatives. And we're going to do that by talking about how to optimize airports and how to do whisky with computers. Funnily enough, that's possible today. So let's see how it works. The talk is going to be roughly in two parts. So around halfway through, I'm going to pass it to Maria, and she's going to talk about how to optimize airports, but I'm going to kick off with applying the context on what do we actually mean when we say applied data science, and how could we do whisky with computers. So laying the groundwork here. We as a company and we as people, we've been pretty busy with applying data science to specific business domains. There's multiple ones in which you can apply it, but these are the ones that have been sort of most familiar to us, and these have been in most demand. So if you go from the sort of far right, machine learning maybe started off or kicked off with like intelligent marketing and sales. How would you do personalization? How would you do recommendations? How would you do marketing mix modeling? We've been doing this for over 10 years now, I think. And it's becoming sort of business as usual. But new techniques are coming in, of course, but the business paradigm is the same. How could we improve sales and marketing efforts? Previously, we did it with something. Now we're doing it with reinforcement learning, but the sort of core paradigm is the same. Then I think the sort of next big thing was intelligent operations. So we started thinking that what would happen if we bring the sort of operations research that we learned in school to the sort of 2.0 version. What does it mean to do operations research in today's world with emerging technology? And that's a big phenomenon currently, and we're working on a lot of projects that are related to this topic. Then a sort of cousin to intelligent marketing and sales, we're seeing a lot of intelligent services. And so not essentially trying to do marketing or sales, but doing really intelligent services that are tailored to the customer, that are tailored to the context, that basically deliver frictionless experiences to the end customer. And this is, I think, a lot of new digital tools are driven by machine learning, at least to some extent, because we want it to be intelligent, we want it to feel like something that you actually want to use. So we want to personalize it in one way or the other. The last two are maybe the new kids on the block. The first one, future R&D. What does it mean actually when we mix machine learning and data into R&D, into creative processes? What does it mean when we go to these creative people and say that, could we actually augment some of the stuff that you do with machine learning and data? And I think that's the most growing of all of the domains. I think R&D is changing the fastest if you look at applied data science. And finally, and this is the one that I've been personally working mostly with, is intelligent organizations. So what does it mean for organizations to go from what technology can I use to solve this problem to how can I be a better organization and more equipped to actually solve these problems as an organization, as people, as roles, as competencies, and so on. So how do we actually design organizations in a way that they're best sort of formulated for emerging technology is the last frontier. And from these domains, I think certain sort of patterns appear, or certain sort of technical archetypes that applied data science is actually about. I already mentioned operations research. So what does it mean to bring that to the sort of 2.0 version? Machine learning is a given, but the final three are maybe somewhat new. So causal inference, I think is one of the main archetypes that is sort of standing out in today's applied data science. So we are moving from sort of traditional BI, data analysis, statistics towards rigorous cause and effect modeling, because we want to be really sure about the sort of strategic decisions that we're going to make as a company. And I think if you would want to learn something in applied data science and you would want to go into consulting, I would certainly opt for understanding causal inference. I think it's one of the main topics that we're going to discuss in the upcoming 5 years. Then the last two, in addition to machine learning, in addition to the other ones, many times we tend to need bespoke algorithms, tailored algorithms to solve really complex problems that we cannot solve with a certain model or architecture type. And this is where I think we mostly need experts currently. So we need experts to solve really difficult problems that are unsolvable with sort of traditional methods of machine learning and applied data science. And finally, the one that's linked to augmenting creativity is generative modeling. So instead of trying to predict the most accurate answer to a question or trying to do something as accurately as possible, how could we create creative machines, which is a completely different sort of paradigm. And it reaches far beyond making products. It will reach how will we design architectures, it will reach how will we design personalized healthcare and so on. And I'm going to delve into that a bit more just ahead. And it's not uncommon for applied data science to being a really sort of first-class citizen for solving business problems. We see like overall efficiency increasing by dramatic amounts, to innovation in fast-moving consumer goods, to increasing RPU in telcos with dynamic pricing, and the list goes on. So there's multiple frontiers in which you can use applied data science, and it's becoming more and more the top management agenda. And if you look at what's happening in the context and in the scene of applied data science, I think one way to look at it is that some of the things are becoming off-the-shelf ready, business as usual, and they are becoming software development. You don't need specialized data science people to solve problems, because the tool set from open source is becoming readily available, and it's really easy in today's world to do recommendation systems. You don't necessarily need a data scientist to do recommendation systems, but you still may need data scientists to solve tailored problems. You need data scientists to solve how to do reinforcement learning in the real world, and so on. So the x-axis is on the right, you have stuff that's complex, non-trivial, something that needs tailored expertise. And on the left, you have stuff that's becoming software development, that's becoming business as usual, and that's sort of merging into the stuff that we do day to day. And on the y-axis, on the bottom, you have augmentation. So instead of trying to replace humans, let's try to figure out how can we sort of coexist in a way that we actually augment people with machines and with data and machine learning. And on the top, you have automation. in its simplest form, the sort of easiest example of automation is recommendations. You don't want people to do customer-specific recommendations for an e-commerce site because it makes no sense. So we want to automate it. But I think the augmentation part is something that's currently driving. So how can we sort of coexist? What does it mean if I have a computer as a coworker? Because there's a lot of sort of UX and design things related to it. It's not just like solve the problem, because it's so innate to us that we feel that computers are worthy of only certain tasks. And it may become increasingly difficult to say that computers can also be creative. And today we're going to talk about two things. One, on the bottom right, AI-assisted creativity and generative modeling, and then logistics optimization, how to run an airport when you run it with applied data science. And we're going to start off with the first one. So generative modeling, computational creativity, it's been around the block. Obvious, which is the brand behind all of the computer-made arts, made a partnership program with Nike to design tailored sneakers. How could we sort of envision new designs for one of the most known sneaker brands? And I think this is somewhat interesting. But what really sort of caught my eye in applying sort of augmentation to and applying creativity to machines and machine learning was this example for architectures. Because if you think about the problem with architecture currently, is that if you want to design something, designing something is super difficult. There's so many constraints, there's so many things that you need to consider, but you still, the way you want to interact would be simplicity. So you always need an architect to support that. What if it would be possible just to paint something that you want, and the computer would be able to then sort of dictate what's the right type of structure, what would be the ideal sort of floor plan if this is what you want to do, and so on. Because this creates a lot of opportunities if you think, what if we would be able in the future to co-create an entire building? What if the residents of a specific building would be able to co-create it with machine learning, with modern tools, with emerging technology? What would that mean for the entire construction business? And I think that's somewhat interesting. And that's why I want to talk about whisky. And this may seem like a stretch, but I assure you it's not. Because the sort of core paradigm behind it, it's the same. We started off the whisky gig with visiting Gävle, which is the place where they make whiskey for Mackmyra, which is a Swedish whiskey brand, in which I wanted to learn how to make whiskey. The woman on the left is Angela Doratio, who's the master blender or the chief nose officer at Mackmyra. So she's the creative expert of the company. And I tried to pick her brain on how do you make whiskey and how could we actually use machine learning to do so. And whiskey in their case is a blending problem. So they have a single liquid, but they put it into different casks. So they have 100 different cask types, ranging from champagne casks to Swedish oak casks to smoky ones. And we put the liquid in, we sit it for 6 to 10 to 12 to 20 years in there. And then we want to blend these in a way that we create the perfect liquid, we create the perfect product. And it's somewhat difficult because when you start thinking about it, it's a complex problem. You have 100 different sort of ingredients that you want to use. And basically how master blenders do this is based on decades of experience. So they smell stuff, they taste stuff, and then they realize that, okay, A mixes with B pretty well. Funnily enough, we can't do that with computers. So we need to figure out a different way of solving the problem. So I'm going to walk you through. Here's 100 casks, just visualized. What you know is that you need to pick from 1 to 20 out of those casks and mix them in a way that you have a recipe that's the perfect blend. You also know from data from previous recipes that, okay, recipe A was really preferred, it sold well and so on. Recipe B was maybe not so well behaved in the sales frontier, but it was preferred by the general sort of whiskey community and so on. So you have certain data points on previous stuff. And exactly, we had 70 data points. So we had 70 previous recipes that we could use. So that was the sort of data set we could play around with. And here comes the problem. At this point, at least, you realize you're a computer nerd and you need to solve this without tasting anything, and you need to solve it in Python. You could solve it in other languages as well, but that's the only one I can use in a way that I can actually make whiskey with computers. And you also know that there's an infinite amount of possibilities, right? Because there's hundreds different ingredients you can use from 0 to 100% from each of them. The blending problem becomes infinite in terms of possibilities. So you start figuring out, okay, what do I need to do? I have the original recipes, I have the reviews, I have the awards, I have some data on that. At least I need to know how to decide casks. I need to be sort of sure on how to decide amounts. I also need to know how to ensure that it still sort of feels and tastes like something that they would have done, because we don't want to do something that would be too far off from the brand, which they have been building for like dozens of years. But we cannot also replicate anything that they have done. So it's a problem. So we need to be creative, but we need to be creative respective with the brand and its feel. Then we also need to be able to discriminate. So based on the cask, the amount, the current recipe, we need to be sure on how do we evaluate that? Is it good? Is it bad? Is it better? Is it worse? And so on. And based on that information, we should do iterations. So if one iteration is better than the previous one, okay, let's continue on that. If it's worse, let's go back a few steps and try again. And let's try to design this as a computer program. And don't worry, I'm not going to go this through entirely. But basically, if you want to take a screen capture and go and make your own whiskey, this would be the slide, I think. So we used different sort of specific learning algorithms in the process of creating whiskey, and we used the modern architecture. So we used a GAN architecture, but we used the sort of bits and pieces of that as specific learning algorithms. So we used fairly traditional ones. We used decision trees. We used Bayesian stuff for deciding amounts. We used matrix factorization for ensuring a fit to the brand, and so on. So there was a lot of different things that we it was like solving a puzzle, right? So it wasn't like one model that would do the job, but we wanted a tailor-made solution so we would have control over specific parts of the problem. And ultimately, what it looked like is that we run this thing for millions and millions of iterations, and what comes out is recipes or recipe candidates, if you want. And from these recipe candidates, we want to know, are they something that we could actually put on the shelf of different stores? And we did this twice. The first one was basically a trial run. So let's just try it, see if it works. And we sent the recipes to Angela, who's the master blender. She said that this is great, but you're using too expensive ingredients. So we put some constraints in that we're not using like 100% of champagne casks because they have really limited amounts of that. And then run it another time. And then based on that, we got around 30 recipes. And from those 30 recipes, we picked 5 ones that we wanted to sample. So we wanted to understand, how does this actually taste if we blend it? If we take the stuff we get from Python, we blend it and taste it, see what it tastes like. Funnily enough, one of the recipes, I think it was recipe number 15, went directly into production. So without changing it in any way, one of the recipes that we sampled was so good that, okay, let's just put it into production. Because as I said, doing computational creativity is different than searching for the ultimate goal or searching for the most correct answer. We're trying to build a machine that has similar creativity than a human has, in a way that it would be able to do a bunch of recipes that all are like good enough to try. And the one that we put on the shelf is labeled intelligence. And I'm going to note 3 things about it before we move to optimizing airports for Santa Claus. Number 1, we got a higher average rating in WhiskyBase, which is the largest sort of whiskey rating site. We got a higher average rating than the brand itself in its average. I think that was pretty cool. So it was preferred by the public. But there's 2 biases. Bias number 1, I like it because it's made by computers. Bias number 2, I hate it because it's made by computers. Both are sort of at play here. What was much more important to me was the master blender. When she said that, that's nice, I would have not thought about this myself. Okay, now we're getting somewhere. And this is maybe my point on, because we're going to see a lot of computational creativity in the years to come, is that we can bring in stuff based on data and machine learning that's interesting even to a seasoned expert. And I think that's saying something, and that's pretty cool. But what's the thing I want to leave you with is that our ultimate goal when we started making whiskey with computers was that we, in a way, we want to show the middle finger to the whiskey industry. They don't think that you can use computers, data, machine learning, data science, what have you, in any part of the whiskey making process. So we wanted to win a blind tasting. So in the American Distillers competition in 2020, we won the gold medal in our sort of division. And I think that was super cool, because that was then saying something. I'm not saying that we're going to make whiskey only with computers now. I'm just saying that it's an interesting possibility, and it's coming to other industries as well. We can certainly make machines creative in a way that they can actually augment seasoned experts. And that's what I want to leave you with on the first part. So now moving to how to optimize airports for Santa Claus. Over to you, Maria.
Okay, so hello everyone. My name is Maria Pusa, and I'm going to tell you about this project that we did with Finavia. So Finavia owns and operates all the airports in Finland. There are 21 in total. And before COVID, there used to be 25 million passengers. And Helsinki is, of course, the biggest of the airports. However, our project was related to this tiny airport of Kittilä in northern Finland. And the obvious reason for that is that's the home of Santa Claus. And for this reason, it becomes really popular during the Christmas season. So during summertime, there's typically only 1 flight per day to Kittilä. But as Christmas approaches, there can be as many as 60 flights per day. And since it's a tiny airport, they have been really struggling with their limited resources. And here are a few pictures to illustrate just how popular it is during Christmas time. So on the left-hand side, you can see that all these planes are approaching Kittilä at the same time. And on the right-hand side, you can see that the airport really is packed with parked airplanes. So how do you operate an airport in these kind of conditions? So generally, the operations of an airport are built around so-called parking plan. So a parking plan states where each plane at the airport is parked and when. And all the other operations, such as ground handling or baggage handling, then just follow this plan. So Kartela is a tiny airport, so there are only 12 parking stands, and there can be as many as 58 flights. So the question here is, how do you assign these flights to the parking stands so that the plan is as efficient as possible? So planning the parking might sound like it's pretty straightforward, but it's actually quite complicated. And I'm going to talk about these challenges next. So first of all, not all planes are allowed at all places, but there are several rules and regulations. So at bigger airports, there can be as many as thousands of rules, and that's why they usually have a dedicated rule checking software for this purpose. But at smaller airports, such as Kartela, everything is just handled manually. So practically, this means that the person who is responsible for the plane parking just needs to memorize all the rules and then apply them on the go. Secondly, there are restricted resources that needs to be taken into account. So we might have the most perfect plan for the following day, but if it requires, say, more buses than there are available, it is actually quite useless. So at every time step, we need to make sure that the plan doesn't require any more resources than there are actually available. And these resources include the stands, of course, buses, check-in counters, staff, you name it. Then thirdly, we have preferences. So these are the things that are not absolutely mandatory, but that we want to make happen. So these can either make or break the plan. So for example, we want to make sure that all the transfers run smoothly, that the walking distances of the passengers remain reasonable, that all the resources are being used in an efficient manner. And also the airlines do have wishes, and it is a good practice to try to take those into account. Sorry about this. Seems to be stuck. Okay, then one problem is uncertainty. So there are some variables that are uncertain. So to me, it was really surprising to find out that, for example, passenger amounts are not usually known beforehand. So how can you plan an efficient parking if you don't know how many passengers are going to be on each flight? So that is a real challenge. And a real challenge is also that the flights are always late. So statistically in Kartela, all the flights arrive late. So it's really difficult. You spend hours preparing a plan, and then it can happen that the first flight of the day arrives late, and then the rest of the plan becomes useless. So that's a real challenge. And then finally, planning the parking is difficult just due to problem dimensions. So although Kartela is a tiny, tiny airport, there are so many alternatives that we couldn't compute them all, even with the supercomputer. And this is how they used to do the planning in Kartela. So they just used a pen and paper. So this here is a real plan from before our project started. And it used to take them 3 hours to prepare this kind of plan for the following day. And now, even after the plan has been completed, it is quite difficult to answer all these questions that are quite crucial to operating the airport in an efficient manner. And also now imagine that one or two flights arrive late. How do you update and maintain this plan? And how do you communicate the changes to the airport? It can be a bit stressful. So all these changing happen all the time, and you need to maintain that plan throughout the day. And usually there's very little time for making the new decisions. So this is actually a direct quote from the head of airplane parking in Helsinki, and it illustrates well what kind of job this really is. Now, what if we could use mathematics to produce the optimal parking plan for an airport? Well, it turns out we can. So this is what we did. We created a linear optimization model, and this actually made Kartela the world's first AI-optimized airport. And this is how our solution looks like. So first we took all the flight and airport data and used it to create predictive models for the missing variables, such as passenger amounts. This data and the models are then used to construct the optimization model that then produces automatically the stand allocation plan. So the optimization is based on an iterative method where we solve a main problem and a subproblem. So in the main problem, assume that we already have some generated sets of possible parking plans. So not the whole search space, but some subset of that. And from that set, we're trying to find the best possible combination, taking all the constraints into account. So mathematically, this can be formulated in the linear programming framework. In the subproblem, on the other hand, we're trying to find new parking plans that have the greatest potential of reducing the total cost of the main problem. And the way we can do this is that we take the so-called dual solution from the main problem and input it to the subproblem. And this can be presented in the shortest path problem framework. And when new, better alternatives can no longer be found, we know that we have converged to the best possible solution in the LP framework. At this point, we do one additional solve. So we just constrain all the variables to be binary, and we solve it as a mixed integer problem. And for Kartela, it actually turned out that these solutions always match. And that is how we know that we always found the true optimal solution. And this is how the solution looks like, visualized in the UI. So in Kartela, they wanted to use iPads for parking planning. So this is what we did. So here the numbers represent the stands. So there are 12 of them. And the bars here correspond to the times that the planes are on the ground. Next, I walk you through to the solutions to the challenges that we talked about previously. So first of all, we have rules and regulations. So now that we're using an optimization model, we can just add these as optimization constraints, and then we don't need to worry about them, because every solution produced by the optimization model will automatically fulfill these all. And the same actually applies to restricted resources. So once they have been included to the optimization model, no need to worry about them. What about preference system? Well, these are actually used to build the cost function to the optimization model. So these now determine if the plan is good or bad. So in that way, they're also automatically included. So the right way to tackle uncertainty is to use predictive models, because in this way, we can be sure that all the decisions are based on data and not just guesses or hunches. And then what about unpredictable changes? So this is a tricky one. So luckily, robustness against changes is something we can actually define mathematically and use in the cost function. So from all the solution space, we can find the single solution that is as robust against changes as possible. Of course, it can happen that it's a super busy day and several flights are delayed. This is still not enough. But in this case, it is then really beneficial that we can just create a new plan with a click of a button. And then finally, some delay here again. Thanks to a tailored optimization algorithm, we don't need to search the whole solution space, but we can converge the best solution in less than 30 seconds, just using a normal laptop. And then I'll show you some examples for Kartela. So here you can see a schematic of the airport with all the 12 stands. So for Kartela, the most important optimization criteria turned out to be robustness against changes, and then minimal number of bus transportations. And in terms of buses, Kartela is a special case because the airport only has 4 of them. So if we had used this as a hard constraint, this would lead to no solutions being found during the peak season. So for this reason, we just try to minimize this number, and then the airport tries to rent the additional buses. So here is now an example. So this is a day before Christmas Eve, and this is typically the busiest day of the year. And this plan here has been optimized with respect to robustness alone. So we don't care about anything else. We don't care about bus transportations. We don't care about airline switches, just robustness. And as you can see, this plan is pretty robust. So how you can see it is that the idle times between successive flights are relatively long. So this means that if one of the flights is delayed or one of the flights arrives early, we don't run into trouble. However, the problem with this plan is that it requires 64 bus transportations, and that is way too many. They would need to have at least 7 or 8 buses to actually survive this day. This U here refers to unassigned. So unfortunately, there wasn't enough space for one plane. So there's nothing we can do about that. So what they need to do is that they just need to park this plane outside the official parking area. No can do. Okay. Here's then a second example. It will start again. Waiting for the slide to change. Okay, so another example, and here we have optimized with respect to bus transportations alone. So as you can see, the number has dropped to 38, which is a really good improvement. So what has happened here is that these stands from 11 to 15 are now in a heavy use, and this is because they don't usually require a bus transportation. But on the downside, the idle times between successive flights are now relatively short. So this plan could easily snowball into chaos if 1 or 2 flights arrive late, which is likely to happen. And then finally, here's a plan that's a compromise between these two. So we've put an equal weight to robustness and bus transformations. And as a result, the number of required bus transformations has increased only a little, so it's now 42, which is still really good. And also the plan is pretty robust. So to my eye, this looks really good. And this also reflects the one that they're currently using in Kittilä. And here are some numbers of how we've done so far. So this solution was deployed in December 18. So we are comparing to the previous winter season. So during that time, the number of flights actually increased by 46%, so that's a lot. But despite that, we were able to cut down the duration of average airport-related flight delays by 39%. And also, we were able to decrease the number of them by 50%. So it's a huge improvement. So to put a monetary value to this, in December 18 alone, this corresponds to €500,000 of savings. So it's really significant. And in addition, the airport's NPS score that describes customer satisfaction increased by 20 points. So overall, they have been really happy with this solution in Kittilä. They said that they never ever want to go back to working with just a pen and paper. And what has happened since? So actually, we have been able to scale the solution to Helsinki. That is a much bigger airport. Of course, the aviation industry isn't exactly booming at the moment, but just hope that this will change soon. So thank you for listening.
Cool, that's amazing. I really wish Zoom had kind of a make a pause sound feature. It always seems slightly anticlimactic after all those things you went through that we aren't seeing cheering people, though I'm sure the people in their rooms at home are thinking that. Cool. So we've got some time for some Q&A. We've got some already coming in. This one's from me though, and I'm very interested to get your response to it, Maria. Like you talked about, building a mathematical model to optimize an airport. How do you convince yourself that it's going to work when it comes to Christmas? Like I guess like you're like, okay, there's children depending on this, like, there's going to be tears before bedtime if somehow this scheduling algorithm has a bug in it. How do you know before you get to that critical point in the year that it has a good chance of not stuffing up, basically?
Well, actually, we didn't have that kind of time pressure. It only took a few months to get this into production, and we started like already in August, I think. And also, I had already tried this algorithm for Helsinki before that. So in that sense, I was quite confident.
Okay, so you managed to find a way to, well, because of the way you were developing it, you managed to do it at lower traffic times of the year so that when it did become critical, you already had pretty good confidence that it was working really well. Cool.
Yeah, luckily.
Yes.
We didn't start in November.
Well, I don't know about luckily. You should get credit for planning it well, maybe. Cool. So I've got a question from an audience member, Irene. There's two parts of the question, so I'm going to ask them separately, actually. What areas and use cases do you think would benefit most from using data science that are not using it now? Either of you could answer that, maybe it's speculative.
I think, I mean, as I said before, I think R&D is one of the big ones, and maybe I would be so courageous that I would say that any industry or any function that says that this is so difficult in this industry, in this function, in this and that, it is impossible to use computers. Okay, because you said that, I think the problem is so complex that you would want to use computers, right? So I think like that's one bit of it. The second bit is that when you say applied data science, when you say creativity, you immediately think like arts and music and so on. But I think the more traditional industries is much more interesting, where you have a creative element, but that's not what the industry is about. So like media, for instance, what does it mean to do public broadcasting? What does it mean to do public media in 5 to 10 years? Is it completely personalized to all citizens based on what you want to know, what you want to do, and so on, what are your preferences and so on? I think it's going to be a dramatic change, and we're not really even seeing how that actually works. But I think like the older the industry, the more sure it is that like computers will change that, and hopefully for the better, and not through automation, but through augmentation and the sort of coexistence of man and machine, I think.
Right. Yeah, I think people really appreciated that distinction of automation and augmentation. So I'm going to push you a bit further on one of that, because you mentioned music, and so obviously Sweden is very famous for producing whiskey, but Sweden is also maybe even more famous for producing pop music. Like, do you think that because I guess in pop music is a kind of a problem where you need to absorb a lot about the trends and tastes of the market. There's actually a very kind of potentially data-driven aspect. Do you think that that's an area that will be, or even maybe has already been taken over by augmentation, probably not automation?
Yeah, maybe even both, because if you think like there's multiple ways and there's multiple contexts for music. It's not only the sort of the festive one, or let's go to a lot sort of let's go to a live setup to watch on the pub. But it's also like there's ambient music, there's stuff on the background, there's stuff for cafes and so on, which I think to some extent, why wouldn't that be automated? If like, let's just create endless jazz music for a cafe. Like, why wouldn't that work? Because you're not listening to the songs, you're listening to the friend that's across you. So I think there's settings in which you can do music, even automated. And there's certainly settings in which you can do augmentation. And I think both will be sort of prevalent. That if it's going to be Sweden that's going to do augmented pop music, I don't know. It can be Finland too, because we were the higher up in Eurovision if you watched it. So
very good. Well,
I'm rooting for Finland in this case.
Well, I hope so too. I guess I was just following possibly the machine learner's fallacy of looking in the past and seeing that kind of scientific pop music has come out of Sweden possibly more than other places. So I hope that you're right, Jarno. Cool. So the second part to Elena's question was actually interesting. I hadn't heard this asked before, which is, are there any areas where machine learning or data-driven systems are used that are not adding value? In fact, they're mistakenly being applied, and you think people should back away from using that methodology?
Churn predictions. If you want one, churn predictions is a specific thing that everyone does, especially telcos and media companies, like any subscription company. Yeah. And it's always done in a horrible fashion, because you're just like, basically you're taking the past and what's happened and just like putting that back in your face in the future. It would require a completely different setup, I think, so that it would actually increase or improve the customer experience. And I think if I would stop something, I would stop churn predictions. Yes.
Good. It sounds like you have a history with churn prediction. I won't ask you those.
I do. I can continue on that on another day. Yes.
Maria, did you have any idea of an application that kind of is not really successful, or maybe people are using it when it doesn't really work? Or is churn prediction?
I don't think I can add anything to churn prediction.
Yeah. Cool. All right. Thank you very much, Irena, for asking that question. I've got a nice provocative question next from Mark Chamberlain. So I think, Jarno, he's looking at your example where you described using AI for architectural design of a building. And obviously, one of the things that we are famous for in software is appropriating the term architect and talking about ourselves as architects. I guess it's a metaphor, or maybe it's reality, who knows? There's a lot of arguments there. But could you see those similar approaches being applied to software engineering and programming, and maybe either replacing or fundamentally changing the work that the programmers in this audience do?
Yeah, I think that's a good question. I think the work of software engineers will certainly change, but I don't think it's going to be automated. I think two things are going to happen. One is that sort of machine learning applied data science will become standard in most sort of software engineering, because it's an elegant paradigm to solve problems. We've been sort of hyping it in a way that it feels sort of weird and complex, but it's really not. Because if you think about that, I want to program a car that can drive itself. Like, how hard will that be if you use like if and else statements? Like, there's no way then to use machine learning. So one thing is, machine learning data science will merge into software development. And I think another thing that's going to happen is that software development will not be automated, but it will become a sort of citizen skill in a way that like in like basic school, like in addition to English, you will learn computer science. Because it's a way to communicate, it's a way to create, because when I was back in school, I was doing stuff from wood, and that doesn't seem like too handy today, because I do appreciate the skill, but I would have loved to learn computer science back then. So I think it's becoming a citizen skill. Machine learning is sort of merging into it, so it will be broader in terms of accessibility, and it will be more deep in terms of what you can do with it. But I don't think it's going to be automated, and I don't think machine learning will sort of change that in any other way than bring more tooling to it.
I think you make a really good point about kind of what already exists with machine learning. So if I think of decision trees, which I guess is something that you use in your work, decision trees really are an augmentation from saving a programmer from having to manually identify boundary conditions, right? Like, I have seen systems that are those if then else's written manually, whereas actually that work of working out the boundaries of different cases is probably not the best use of a programmer's time. And if they had the right data to drive it, they could have avoided it. So maybe it's already happening that certain repetitive tasks in programming are being eaten away by machine learning techniques.
Yeah, certainly.
Cool. So I have one for you now, Maria. Jarno is obviously quite good at hyping these things, right? He even mentioned it himself. So how do you feel when people use the word artificial intelligence all over the place, right? Like almost everything, if you want to raise more funding for your startup, you say it's an artificial intelligence startup. When I look at the work you're doing, it's very deep, very technical, and it's kind of, but it's, you know, it's operations research. And so I don't necessarily associate the term AI with that. Do you think that using that term AI is helpful or unhelpful for the kind of work that you're pioneering?
Well, I think it's definitely both. So if we didn't talk about AI, I think no one would be interested in my work.
Right.
But of course, it can be misleading in that sense that it makes people think that there's something besides mathematics in these kind of solutions, but still it's all just mathematics. So that's how I see it.
So you can kind of use the hype, you know, if you're trying to get someone interested in your work, or I guess meeting someone at a party, you say AI. But then when you're trying to explain to someone how to do it, you say, oh, it's linear algebra or something like that.
When you say you're a mathematician, people automatically get bored.
It makes sense. Cool. All right. We have probably more questions than we'll be able to cover in this talk. I think we can go for another few minutes, and then there'll be a break and the next talks will start. But for any questions I don't get to, I'm going to chuck them in the Slack, and there's already some conversation, most of it, I must admit, unhelpful in the Slack so far, but there will be room for some good answers there too after this talk. So we've got another question from Irene, which is around bias in your models. So I guess not bias in the sense of the bias term in the bias in the sense of bias in data sets causing or correlating or reinforcing social biases. So Irene's question is, how do you make sure there's no bias in your model? Bias in the sense of, you know, Google's face recognition algorithm treating black and white faces differently, for example. Like how do you, A, how do you satisfy yourself that you don't have that? And B, have you encountered a situation where you have detected a problem of that kind in work that you've done?
Yeah, I can maybe start because I think it was interesting. It was Netflix that posted the blog on the topic that they were accused of being racist, yet they don't ask for race when you subscribe to Netflix, which means that from the implicit viewing behavior of people, you get the result that seems like it's racist in its behavior, which poses a problem that, like, actually, if you really want to eliminate bias, I think there's two ideal ways. The first one is that you actually need the information that you want to be unbiased about, because otherwise you can be implicitly biased. The other solution is to use enough sort of randomization, enough exploration in the systems in a specific loss function that sort of discriminates against biases to do so, I think are the two main ways to tackle it. For instance, for Yle, which is the national broadcaster here in Finland, we did a reinforcement learning system that like, if you don't know reinforcement learning, the core idea is not to learn from like all of the past data for the sake of it. The core idea is to interact with the environment and learn from all of those interactions and do controlled exploration of all of the possibilities for all of the different sort of contexts, which means that for every single type of customer, everyone gets all of the alternatives at some point in time. So I think like exploration is one, and the second one is that we need to know what we don't want to be biased about in order to tackle it, because otherwise implicit bias, especially when there's a lot of implicit data, is a real problem, and it's a problem we cannot tackle without knowing, without sort of asking people about the specific thing that we want to be unbiased about. So it's certainly a problem, especially for the sort of AI ethics talk, because we want to know the thing that we want to be unbiased about, which is a problem when you state it out publicly.
So your answer reminded me almost of that joke about XML, which says that if XML hasn't solved your problem, you need to use more XML. So I like your answer is, okay, if we have bias, we can build that. Well, part of your answer, which I thought was really interesting, is we can build it into the loss function. I guess that is something that we can do if we have explicit protected characteristics or so on, which is, you know, how we handle the problem in discrimination in society. We say it is not acceptable to not hire someone because of, you know, gender identity or race or things like that. But I guess your earlier comment about machine learning being a citizen skill comes into play here, because although I very much like you, Jarno, and you, Maria, I also think that these conversations should not be had just by people from within the field. If there's a wider understanding of the implications of machine learning and what strengths and weaknesses, society can actually have a bit more of an educated conversation about it. In the end, you know, programmers are smart people, but we haven't always shown ourselves to be 100% self-aware, let's put it that way. Cool. So I have one more question, or maybe I'll get to two, but I have one more I'll ask now. So Leonardo is asking, what's the correct path for a Python backend developer to get started at ML? I guess Leonardo's been inspired by the examples you've seen and wants to know what you'd recommend to start getting into the field.
That's a good question. I'm not sure what Maria would answer on this, but like at least for me, I think there's a lot of like really good sort of online sort of massive online courses that you can take. I can certainly recommend machine learning courses from Stanford, and this is now a biased answer. I just prefer them. You can select anything else you want.
Yeah.
But like my preference would be to have the intro course from Stanford and then just take a whack at it on a specific problem that's related to the current company, industry, whatever that you're working on, because it's not that complex, really.
Cool. I guess, yeah, experiment and give it a go. Actually, like, you know, get your hands dirty as part of successfully doing that.
Yeah, because again, the sort of the most known problems are relatively well tooled at this point in time. So recommendations, time series analysis, and so on. There's loads of information that you can consume.
Sure.
And you know, after this talk, you can also try to make whiskey if that's the case.
Well, I invite people to put their favorite courses and whatever in the Slack channel. It'll probably be good for following up. So I'm going to end by just asking Maria a complementary question. So I guess, Maria, if you're someone who's a mathematician or a physicist who's good with like numbers and stuff, how would you recommend getting into this kind of operations research applied intersection with programming field that you're part of now?
Yeah, that's also a quick question. Well, maybe the first thing would be to learn Python and something about cloud computing. And then, as Jarno said, there are loads of material. So it's easy to get your like hands-on problems and then just try solving them.
Cool. All right, almost convergent. The answer, all roads lead to Python, that sounds like. Cool. But yeah, I think, you know, certainly from my experience, the skill set of people who have deep strength in mathematics and understanding these concepts really can make big differences when we're getting into complex fields like the ones you've talked about.